So in hidden Markov models, there are three central algorithms, maybe more actually, but central that are easy to use and easy to understand. And one is the Vitterbi algorithm. And one is something called the forward algorithm. And one is called the backward algorithm. And I'd like to at least make sure that you understand these two. This one is slightly less important, and it's in the notes that I handed out. But given time, we'll see if we get to it today. Okay, but the Vitterbi algorithm solves the following problem. Given a sequence S, x1 through xn, and a hidden Markov model, okay, a hidden Markov model that generates some family of sequences, some family of sequences. And remember that because it's a hidden Markov model, there are different Markov chains that can generate the same sequence. Okay? So I'm going to say here's sequence 1, sequence 2, sequence 3. And sequence 1 might have been generated by more than one Markov chain. Okay? Some set of Markov chains that could generate sequence 1. So sequence 1 is associated with some set of Markov chains in that hidden Markov model. And sequence 2 is associated with some other set. Maybe I should subscript this like that. MC21, MC22, MC23, MC, and so on. And each one of these Markov chains has some probability of occurring. Okay, remember how the Markov model works. You start in the start state, and then the edges out of it each have a different probability. So if there are 5 different edges out of it, you flip a 5-sided coin, which has a probability of landing on a particular side depending on what those probabilities are on the out edges. Then you move to the next state, and you again, according to the probability distribution on the out edges, you move to another state, and so on. And every time you're in a state, you emit a character. Now, you may emit that character deterministically. That is, that one state definitely is associated with some particular character. Or what you actually emit may itself be a random variable. It's according to some probability distribution. Okay? But anyway, you're walking around this Markov model. It's a Markov chain generating an output sequence. And therefore, every sequence, every Markov chain has a particular probability of being seen. There's a certain frequency in which it occurs, and therefore there's a certain probability that's associated with that Markov chain. So this is the probability that when you put your quarter in the Markov model and let it run once, what's the probability that you got out MC11? Okay? So what's the problem again? Given S and a hidden Markov model that can generate some family of sequences, find the Markov chain. It's also called a path in the hidden Markov model. Find the Markov chain which generates S and has largest probability over all Markov chains that generate S. Okay? So that's your best guess at how S came about. I mean, You put your quarter in the Markov model. It starts doing its thing. Out comes a sequence. And you want to say, if I had to gamble on what Markov chain it was that generated that sequence, which one should you bet on? Well, you should bet on the one that has the highest probability of being the one that did it. I mean, it's no certainty, but your long-run average correctness is going to be best if this is what you bet on. And why do you want to know what the Markov chain is? Because the Markov chain tells you what states were in the plus model, the GPC island model, and what states were not. And then from that, from knowing that Markov chain, you say, well, I gamble, I think, that the states that were in the plus model correspond, those are the states that are emitting certain characters of the sequence. It's those characters in the sequence that are in a CPG island. Okay? Or if you have a Markov model for some other feature or motif, then it's your gamble is that portion of the sequence corresponds to that motif. Okay? And databases like PFAM have, I don't know, 2,000 or 3,000 at this point, hidden Markov models in there of significant biological motifs or signatures or whatever you want to call them. All right? They're each different little hidden Markov models, and you run your sequence. You solve this problem for each one of those different Markov models, and if the probability that you get out is high enough, and there's also an e-value involved, but you think you hopefully know a little bit about that by now, then PFAM reports that S might have that particular motif or might be from a particular protein family that was used to generate those motifs. Okay, but this is the problem. Find that Markov chain which generates S and has the largest probability of all Markov chains that generate S. Of course, it could be probability 0. Maybe there is no Markov chain that generates S. You certainly would want to know that too. And we described last time how to do that. That's solved by the Viterbi algorithm. Okay? But it's just straightforward dynamic programming. And I'll try to go through this again. And so we define V. I've always forgetting what the notation they use in these notes is. And it is simplest if I maintain the same notation. Okay, so V Li, that's defined to be the probability of the most probable Markov chain that generates S. Okay, over all the Markov chains that generate S, this is the probability of the most probable one. Well, actually, it doesn't, it generates X1 through Xi, just the first I symbols of S, okay, which ends in state L. So each of the states in the Markov model has an index, 1 through whatever. And we want to know if I focus on a particular state in the Markov model, state L, and here's the start this is the start state of the Markov model. Over all those different chains, they all do something different. All the different chains in the Markov model which end in state L and have generated along the way X1 to Xi, there is one chain, or maybe there's a tie, but anyway, there's a chain which has the highest probability over all those chains that end up in L and have generated this. And I want to know, this defines, this refers to the probability that's associated with that most probable state. It's just the product of all the probabilities along those paths, okay, along those edges. So that's what that is defined to be. So we want to compute that by dynamic programming, which means in the end we're going to build a table like this, which is going to have states. Start with our begin state, down through however many states there are in the Markov model. Let's say they're M. And it's going to have characters. This is before any characters in the actual sequence. So we're going to end up with a dynamic programming table like this. And here, Li, so state L, character I, is going to be put right there. Okay? Now, when we were dealing with alignment, our alignment was sort of similar too, because, or a philosophy for alignment, because we were taking prefixes. We were taking prefixes of two sequences. Now we only have one sequence. And whenever we wanted to fill in a cell in the dynamic programming table, we had to look at three neighbors. Okay? But it was some finite number. We'll see in this case that you have to look at more than just three. But nonetheless, the philosophy or the general approach in dynamic programming is to try to explain how I would get this value if I knew the values for some smaller indices. Okay? Smaller in some way, mostly having to do, in this case, having to do with smaller prefixes. Okay? So here's how we're going to think about getting the recurrence relations. First of all, we need the simple ones, the basis, the simple recurrence relations. If you're in state, the begin state, and you've so far generated nothing, what's the probability of the most probable path that does that? It's in the begin state and it generates nothing. And first of all, how many paths do that? 4 or 5? Well, they all do that in a sense, yes, but they're all described the same way. They're in the begin state and they've generated nothing. I mean, there's not much diversity there. They all look the same at that point. And the probability is 1. Okay, that's essentially saying they all do that. What about some state K, or I've been using the index L, that's not the begin state? Okay. But it's generated nothing. Well, in our Markov chain, our hidden Markov models, every state emits something. We don't have any, in our models we've looked at so far, we don't have any states that are called silent states. In a richer model, you can have silent states where the state does not emit anything. So this is saying if you're in a state other than the begin state and you haven't emitted anything yet, that's not possible, so this is a probability of 0. Okay? So those are the two simple cases. In all dynamic programming, you start off by thinking about the really trivial cases. All right? And so, in fact, what that does is it gives these values along here. Right? Oh, and I guess we should have ultimately an end state, or whatever. And with an end state, by the way, where we're getting the value that we ultimately want is right here. We ended up using or generating. We're no longer using up or consuming characters that's the way we talked about things when we were talking about alignment. Now we're talking about emitting them or generating them. So when you generated all of them and you're in the end state, then we want to know about that probability there. Okay, so the general recurrence is V Li. Okay? So let's go back to this picture. This is the most probable path. And there is some state that is the state just before you go to L. Okay? And we don't know which state it is. It could be anything. Well, as long as it has a non-zero probability of going from that state to L, it could be anything. So, but what we want the max over all possible states K other than L. Well, actually, no. Markov models have the ability to stay in the same state. So all possible states K, not all Markov models, it just depends on the particular model, but it's not excluded. So we certainly, for generality, we should put this here. Okay. So we know there is some state that's the last state before you get to L. And the whole, the thought process of generating recurrence relations for dynamic programming says, I don't know which one of these states that was the last one along the most probable chain, but I do know how to tell you what the total probability will be if it's this one, or if it's this one, or if it's this one, or it's this one. I know how to calculate that probability, and therefore I will just take the best over all of those, and that, in fact, will be the answer, because it has to have been one of those. So let's say it's this one. Let's say this is state 55. Just for some thought experiment. Let's say you knew for sure that the last state, actually, I guess in this picture it looks like this. Let's say you knew for sure that the last state before you went to L in generating x1 through xn in the most probable path was state 55. Then what would be the description of VLI? Okay? Well, it would be, what's the probability value, what's the product of all those values for getting to state 55 and generating prefix not 1 through I, but prefix 1 through I minus 1. If this is the last state before you get to L, and L is where you emit character I, then this is where you emitted character I minus 1. So that would be V state 55 I minus 1. That's the product of the values along to there. Then what's the probability of going from 55 to L? We don't know an actual number, but what's in terms of notation, does anybody remember from last time what we were using? Is what? Yeah. It would be A 55L. Okay. And then when you get to state L, remember we're trying to compute VLI, which is we emit along that chain the first I characters. So here's where up to here you've emitted the first I minus 1. So here you emit the ith character. What's the probability that you do that if you're in state L? That notation, I think, was EL XI. Okay? So that would be the probability. This would be VLI would be exactly this. V55I minus 1 times A55L times EL XI. If you knew that state 55 was the last one on the most probable path. But you don't know what the last one is on the most probable path, but you do know there is one. There is a state which is the one that was taken on the most probable path just before you got to state L. And so instead of having 55 here and having 55 here, what do you have instead? You can't think specifically. You don't know what state it is, but you can describe it generally, and then that can be used in your computation. So what do I replace 55 with, consistent with this discussion? It's what? No, no, the 55 should not be L minus 1. It's what? K. Yeah, it's a general index for all possible states. Okay? So it would be VL I minus 1 times A, what did I say, L? VK I minus 1 times A KL times E L XI. And that's it. And so if you're here, you're trying to compute VLI, what do you do mechanistically? Okay? Mechanistically, you have to I minus 1 you have to look at all the values along here. This is where you're picking up the V indexed by different states for sequences that end with, that go up to I minus 1. For each one of these values, you have to look up in some table somewhere that tells you the probability of going from K to L, some description of the hidden Markov model. All right? And then you have to, in some other description of the probability distribution for emissions, you have to look up that number. You multiply these together, which gives you a candidate for this one, candidate for all of these. And one of those is the biggest. And whichever one has the biggest one, you write that number here. So you write that number, whatever it happens to be, 0.57. I don't know. And what do you always want to do in dynamic programming so that you can reconstruct the actual solution? In the end, you don't just want a number here. You want to know what the most probable chain was. Okay? This definition is for the numbers, but I want to compute the actual chain, too, because that's going to tell me which sections of the sequence we think are CPG islands and which ones we don't think are CPG islands. So what do you do whenever you compute a number for a dynamic programming cell? Traceback. Yeah, you have to be able to do traceback later, which means it's convenient if you would leave a pointer here telling you what was the K that you used to get this value. What was the K that gave you the max? Okay, max of this. And so in the notes, they use this awful notation. I think this is the pointer, again, for state L up through character I, equals argmax K, and then a repeat of this thing, except they leave out the E because that's the same for everybody, so why bother? Except to just confuse people. Okay, so this argmax means what value of K made this maximum? And that's the pointer you're leaving. You're leaving this breadcrumb back so that when you are here, you can walk backwards. This is actually kind of cool because this traceback actually gives you the Markov chain. I mean, in alignment, it only gave you a representation of the alignment, something you could use to get an alignment, but it was the alignment you wanted. Here, you can just read off the Markov chain in the traceback, except for one detail. What's that one detail? I mean, if you just literally had in your computer program, the Markov chain is, and then you print it out, clunk, 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 as you're tracing this back, what would be wrong with that answer?
Backwards?
It's backwards. Okay. So you're learning the Markov chain, but the most probable Markov chain, the Markov chain that gives you the highest probability, but you're learning it backwards. So you trace this back, accumulating it, and then you flip it around and print it out. That's the Viterbi algorithm. it gives you the most probable path. And if there are ties, just as we did in alignment, you might want to explore all the set of possible tracebacks if there are ties in this, and produce more than one. And for all the same reasons we talked about in alignment, you may even want some paths that are not the optimal but are close to it. They give you some alternative Markov chains that look equally good or almost as good. Okay. All right. So when you hear about the Vitterbi algorithm in the future, you may remember this level of detail. You may, if we had another week of class, I'd ask you to write a program that, I'd have a little hidden Markov model which would give you the AKs and the ELs. And you could write a little, it would take you about 5 minutes to write this program, and it would take you about 3 or 4 hours to debug it. But, at least that's the way I program. But, you could do it in a day. It's not a big deal. It's not such heavy-duty technology. That's what I consider to be one of the easy algorithms. Now, the forward algorithm is the second kind of algorithm that comes up, which is, sorry, was it this question? No. So the forward algorithm is actually, in a way, if you remember, I wrote something last time that I had to erase because it wasn't the Recurrence algorithm. It was really the definition of what you want for the forward algorithm. The forward algorithm takes the view that the most probable path is just one path. It may be too limiting. So actually, there's two ways of thinking about it. Let me just imagine that we're not in CPG island question anymore. We're in a model where the entire sequence that gets generated is a candidate for being the motif, or the sequence. The entire sequence is the sequence of interest. Okay? And then the question is, what's the probability that the hidden Markov model would have generated that sequence? Okay? So now you're going to sum over all of these Markov chains that generate that sequence. So the Viterbi finds, if this is our S, this is the sequence that we actually have in our hands, we're trying to analyze. And the hidden Markov model has several different Markov chains that can have generated it. Viterbi gives the chain of max probability among those chains that generate S. But another question you might want to ask is, what's the probability of S itself? Okay, so you run the Markov model, it zooms around different states. It generates it emanates some sequence. Well, it might be this S, or it might be S2, or it might be S3, or it might be many different possibilities. So what's the probability that you would have generated the particular sequence you're looking at? And that's an appropriate question in several different contexts. In the case of the CPG islands, I guess you could say if we have a very typical set of training sequences that we used in the first place to build the hidden Markov model, some portions of that have CPG islands, some don't. You could ask, when you have a new sequence, what's the probability that our model would have generated that sequence? Or it's probably more appropriate, easier to think about if the hidden Markov model doesn't have subdivided portions in it. It's just a sequence which we believe might come from some family of sequences. And so you want to know what's the probability of that sequence that sequence is generated by that Markov chain, by that Markov model. Got to keep those chains and models separate. The other way people like to think about it is actually the way they state it in these notes I gave you, which is what's the probability of the Markov? What's the probability of the hidden Markov model? Now that question has no syntactic correctness. It's actually what's the probability of a duck? I don't know. What does that mean? But that's the way people talk about it. And what they really mean by that is how good is this hidden Markov model in terms of explaining the sequence that we have in our hand. Okay? Because maybe the most probable path has a teeny probability. It's small. Okay? And is it then the question is it a large enough, is that hidden Markov model really a good model to capture and explain the kind of sequences we're throwing at it? All right? If the Viterbi computation produces a path with a very small probability, you're not really sure. If it produces a path with a huge probability, that's fine. Okay? But that's a different matter. Now, actually, what the let me just read from page 57, because this is the number of possible paths. And they're talking about paths, either the paths or that generate the sequence or not, increases exponentially with the length of the sequence. So brute force evaluation of that probability by enumerating all paths is not practical. Okay. I'm going to skip some words. One approach is just to compute the most probable path. That's the Viterbi path. Okay. This implicitly assumes that the only path with significant probability is that Viterbi path, a somewhat startling assumption, which, however, in many cases is surprisingly good. So what they're saying is, even if you're interested in the question of what's the probability of seeing S, that a lot of times just taking the probability from the Viterbi computation, the most probable path, is reasonable. But in fact, that approximation is unnecessary because the full probability can itself be calculated by a similar dynamic programming procedure to the Viterbi algorithm, replacing the maximization step with, you'll see in a minute, I want somebody to fill in the blank. This is called the forward algorithm. Okay? So, again, the forward algorithm, whereas the Viterbi algorithm was taking the max over these probabilities, okay, the Viterbi algorithm finds the maximum of all the probabilities over the paths that produce the sequence that's in our hands. What we want now in the forward algorithm to do is to compute the sum of the probabilities. This probability plus that probability plus that probability. Okay? So, in other words, you consider all possible paths through the Markov model which produce S. Each one has a probability. Summing them up gives you your overall probability that the Markov model would have produced the sequence in hand. So now that we have, I hope, a clear definition of what we want, we come back over to here. What do we have to change in the dynamic programming in order to be able to calculate that? So I still want an efficient solution because enumerating all the paths is out of the question. The only way we know in this class to get efficient solutions is dynamic programming. So obviously, I'm searching for dynamic programming. Here we have the dynamic programming solution for something that seems clearly related. So always, the right way to proceed in mathematics is to try to rip off somebody else. Do something similar to what was already done before you start investing a lot of time on free thinking. And so how do you modify what you presently know to try to do this? Well, first we would like to change the definitions. And 54, 56. Okay, so they changed the V to an F. I guess V was for Viterbi, F is for forward. Don't ask me where forward comes from. And it's no longer the probability of the most probable Markov chain that generates this thing. It ends in state L. What should it be? You still want to focus on a state at a time and a prefix at a time. You don't know that for sure, but that's the way to stay closest to the dynamic program that you presently have. So it makes good intuitive sense that you try to do that. But it's no longer the most probable Markov chain that generates this thing. It should be the sum of all Markov chains. It should be the probability, it should be the sum of probabilities of all Markov chains that generate x1 through xi and end in state L. Okay, all the possible different ways that you could generate x1 through xi using that hidden Markov model and end up in state L. Each one of those has a probability. It's a product of those paths. Each path, yeah, and then you want to sum up those things. Okay, so the structure of the dynamic programming table is the same. We have states and prefixes. Come over here, the basis. What's F? What's FB0? What's the sum of all the probabilities? Well, we knew one of them was already 1, right? The sum of all the probabilities can't be bigger than 1 anyway. So that is already 1. And what's F? What's that one? What's the sum of all the probabilities of all the paths which end up in some state other than the begin state and generate nothing? In our particular Markov model is 0 because we don't have any silent states. Every state emits or generates something. Okay. And then what's FLI? What do I need to change here? It's what? Okay. Instead of max, you're not looking for the largest probability anymore. You're looking at the sum of them all. So there's sum. When you're in state K, but again, the thinking is the same. If I want to think about all those paths that end in state L, each one of them has a last state that is used before it gets to L. And each one of them, therefore, has some sum of probabilities of all the paths that get to them. So I want to keep the summation over all possible states K, of course. And then this is Fk I minus 1. So this is the sum when we're looking at state K and the first I minus 1 prefixes. AKL, well, that's still there because we're taking this over all Ks. And then ELXI, that's the same also. Because when you get into state L, you have to emit character I. All right? It might have been a little more suggestive if you just take this out, put it there. That's the same thing. Okay, so in this computation, when I'm interested in this cell, now when I'm looking over each one of these, instead of taking the largest, I just sum them up. Oh, and by the way, I forgot to ask you, what's the number of operations, roughly, that's needed when you're doing this, when you're filling in this table? It's the same whether we're doing the F's or the V's, but how much is it? It's what? M times N? Not quite. That's not quite right. N times M was for the alignment. And the reason we got that is there was NM cells, and for each cell you only had to look at a constant number of neighbors, 3. Now, there are NM cells, but whenever I look at a single cell, it's not just a constant number of neighbors, I have to look at M neighbors. Okay? So the number of operations here, by the way, is something like NM squared. It's proportional to NM squared, which is still manageable depending on what N and M is. It's going to get bigger than practical faster than if we were just doing alignment. But you still should appreciate how small this is in comparison to enumerating all the possible paths. If you had to enumerate all the possible paths, you would very quickly, it would become absolutely impractical. And at least one of the nice things about this is that the square relates to the number of states and not to the length of the sequence. Okay? So as the length of the sequences get longer and longer, the number of operations, and therefore the time, is only growing linearly as the sequence gets longer. That's because M is fixed. That M has to do with the hidden Markov model. So for a particular hidden Markov model, as I give it longer and longer sequences, it just takes longer and longer time, but only increasing linearly with the length of the sequence. That's much nicer than if the square was over here on the N. Then as the sequences get longer and longer, the time grows quadratically with the length of the sequences. But again, the key point is to understand that this is reasonably practical for ranges of N and M that are quite interesting and important. And before Vitterbi came along, or before dynamic programming came along, and all people were thinking about was rub 2 sticks together to make fire. No, it wasn't quite that old. But before this whole philosophy, this whole approach came along, people didn't know how they would compute these things. How would they compute these F's or these V's practically? Because all they had conceptually was, well, enumerate all possible paths, and they only had very slow computers. But even with fast computers, there are just way too many paths. It's just impossible. So I want you to come away with an appreciation for what a nice advance this was. And Vitterbi's a billionaire now, by the way, just on the basis of this thinking. He's one of the founders of Qualcomm, which was one of those communication companies which... how many people have heard of Qualcomm? Anyway, so he's one of the principals in founding Qualcomm. And one of their advantages was that they understood this kind of stuff, so they could do fast computations when some of their competitors were thinking about enumerating all possible paths. At any rate, okay, now, in the F calculation, what do we do about this? What do we do about the pointer business? Same. No? Yes, no? Well, it's a trick question. What's the answer?
That's unique.
You what?
I mean, that thing is unique. You don't need a point.
You don't need, yeah, the whole concept goes away because you're not trying to, there's no traceback anymore. You're summing over all possible paths, unless, let's say, you try to enumerate all possible paths, but that would be nuts anyway. So this just goes away because there's nothing to remember. When you've computed the number, that's it. That's all there is. There's no pointers anymore. Okay, that's the forward algorithm, and it gives you some information about how well S is consistent with the, how consistent S is with the hidden Markov model. Okay? So this may be more appropriate if we have, let's say, a hidden Markov model of protein kinases or some fancier class of family of sequences. And then you'd want to come out with, here's my new sequence. What's the probability that it was generated by my hidden Markov model of protein kinases? And that's really what this forward algorithm calculates for you, as opposed to the Viterbi, which is, here's my best guess at what the actual chain was that would generate it. Here's the probability of that chain.